Assalamualaikum and good day. Welcome back to BKS Pakar 2 Construction Technology 4. In this class, we will learn Chapter 2 Soil Improvement and Stabilization Techniques. Let's recap last week's lesson. There are two techniques of soil stabilization, which are mechanical stabilization and stabilization by using different types of mixtures. This week, we're going to learn stabilization by using different types of admixtures. There are 10 of it. Complex stabilization technique grouting is commonly used for subsurface soil stabilization. These include cement grouting, bentonite grouting, chemical grouting, bituminous grouting, and resin grouting. Grouting means injecting the grout or sealant to seal off the cavities, fissures, cracks, or small apertures or pores through which the water can access the intended opening or tunnel, and thereby reducing the make of water to the minimum. In this method, stabilizers are introduced by injection into the soil. This method is not useful for clayey soil because of their low permeability. This is a costly method for soil stabilization. The basic method is to inject the soil or rock with fluids which, on setting, seal or reduce the permeability of the material. The grout used will depend upon the particle size of the soil or the size of fissures in the rock formation. Since this process is costly, it must be carefully controlled to prevent wastage of material. This is achieved by additive in the grout which control the gelling properties, thus limiting their spread in the ground. In permeable soils or soils where it is known that small cavities may be within the ground, pressure grouting may be used to fill the voids. Holes are drilled into the ground using mechanically driven augers. As the augers is withdrawn, cement slurry is forced down a central tube into the bore under pressure. Pressure of up to 70,000 Newton over mm square can be exerted by the grout on surrounding soil. The slurry contains cementitious additives such as pulverized fly ash, PFA, microsilica, chemical grout, cement, or a mixture. PFA is cheap and often used as a bulk filler to improve bearing capacity of the ground. As the grout enters the void, it forces itself into the void cavities and fissures in the soils and rock. In weak soils, it will displace and compact the ground as it fills the void. As the void are filled, the ground becomes stiffer, more stable, and water resistant. Pressure grouting can also be used around basements and cofferdams to reduce hydrostatic pressure on the structure. To create a water-resistant barrier, the bores and subsequent columns of grout are placed at close centers. PFA is generally used as a ground modification and stabilization material, whereas the expensive chemical mix, such as resin or epoxy mix or other containing microsilica, are used to fill small voids and improve the groundwater resistance. Cement grouts can permit silty fine sands, while chemical grouts can permit each finer grained soils but become increasingly expensive as higher permeation is required.
Complex stabilization technique cement grouting. Cement is a mortar which, when mixed with water, can thicken and harden both in air and in water. It is mainly an excellent hydraulic mortar which combines high hydraulicity and strength. Common Portland cements are mainly used for permeation grouting. The basic method is to inject the soil or rock with fluids. Secondary holes are bored between the lines of primary boreholes to ensure complete grouting of curtain. The grout used may comprise of neat cement and water or a mixture of sand and cement in a ratio of up to 4 parts of sand to 1 part cement, which is the most economical ratio. Jet grouting means of consolidating ground by lowering a monitor probe into preformed boreholes. The probe is rotated and the side of the boreholes are subjected to jet of pressurized water and air from a single outlet which enlarges and compacts the borehole sides. At the same time, a cement grout is being introduced under pressure to fill the void being created. The water used by the probe and any combined earth is forced up to the surface in a form of sludge. If the monitor probe is not rotated, grouted panels can be formed. Complex stabilization technique bentonite grouting. Bentonite or clay grouting is used in ground conditions where particles of the soil are too small for cement grouting. While clay adds little to any strength to the soil, it has high resistance to water flow, then therefore produce an excellent barrier. Bentonite is produced from montmorillonite clay, which has thixotropic properties, which is when it coagulates, it forms gel, which is highly resistant to water, and if mixed with certain additives such as Portland cement or soluble silicates, the barrier form will be permanent. It is particularly useful for grouting deposit soils below dam foundation to prevent the seepage of water under the finished structure. Complex stabilization technique, chemical grouting. Chemical grouts such as sodium silicates can set quickly and are the cheapest amongst the other chemical grouts. Other chemical grouts include chrome lignin and polymers. Resin and polymers are the costliest but form of solid mass. For fine-grained sand, chemical grouts of low viscosity can be used, and for very finest sand, expensive resins of very low viscosity may be used, but spacing between holes must be low and injection rates also should be slow. Chemical grouts reduce permeability of void filling and strengthen the ground formation. Complex stabilization technique, resin grouting. The term resin grout is used for grout which are formed by interaction of soluble material. They are of low viscosity, which means the resistance of the fluids to change in shape or movement of neighboring portion relative to one another, and they are formed by adding a catalyst to a base solution. The difference between resin grouts and chemical grouts is one of viscosity. They have a very low viscosity capable of penetrating fine sand in which silicate solutions are little value. Resin grouts include tannin-based grout, phenol formaldehyde, and resorcinol formaldehyde. The type to be used depends to a certain extent on the chemical content of the groundwater. Complex stabilization techniques, bituminous grouting. Large subsurface flows of water are at times difficult to stop by grouting with cement, soil, or chemical grouts. For this condition, bituminous grouting has sometimes been useful successfully, particularly in sealing watercourses in underground rock channels. Asphalt grout has also been used to plug leaks in cofferdams and in natural rock foundation. Asphalt is a brown to black bituminous substance belonging to a group of solid or semi-solid hydrocarbons. It occurs naturally or is obtained as comparatively non-volatile residue from the refining of some petroleums. Bituminous solutions such as cut-back bitumen emulsion can be used as a suitable grouting medium. They can be injected into fine sand to form an impermeable barrier to water. Such solutions are suitable for forming cut-off walls beneath dams and similar structures, but add no strength to the soil. They are applied cold. In the emulsion, the asphalt is dispersed in colloidal form in water. After injection, the emulsion must be broken so that the asphalt can coagulate to form an effective grout. Special chemicals are injected with the emulsion for this purpose. Complex stabilization techniques, stabilization by geotextile and fabric. Geotextiles are porous fabric made by synthetic materials such as polyethylene, polyester, nylon, and polyvinyl chloride. Woven or non-woven and grid form varieties of geotextiles are available. Geotextiles have a high strength which properly embedded in soil it contributes to its stability. It is used in construction of unpaved road over soft soil. Reinforcing the soil for soil stabilization by metallic strips into it and providing an anchor or tie back to restrain a facing skin element. The strength and load-bearing capacity of subgrade and base course material can be improved through the inclusion of non-biodegradable reinforcing material such as fibers, geotextile geogrids, and geocomposites. The major function of geosynthetic materials in relation with transportation engineering are separation, reinforcement, filtration, drainage, and acting as liquid barrier. In providing filtration and drainage, it aids in improving subsurface drainage and allow the rapid dissipation of excess subgrade pore pressure caused by traffic loading. However, the geosynthetic must minimize the possibility of erosion of the drainage layer and resist clogging of the filter over the design life of the pavement. With the application of geotextiles, it helps reduce costs of bringing in earth material from borrow pit. Rather, the initial earth material found on construction site is used for road pavement. Use of these materials can improve the performance and durability of future highways and may reduce the cost of construction. Stabilization by using different types admixture. Chemical stabilization. Chemical stabilization is used for surface soils more successfully. Mixtures of soil and chemical are mixed either mechanically in place or by batch process. For example, the chemical used are lime, cement, and fly ash. The second technique of stabilization using a mixture is cement stabilization. Soil cement stabilization is soil particles bonding caused by hydration of cement particles which grow into crystals that can interlock with one another, giving a high compressive strength. In order to achieve higher bonding, cement particles need to coat most of the material particles. This to provide good contact between soil particles and cement, thus efficient soil cement stabilization. Mixing the cement and soil with certain particle size distribution is necessary. Soil cement is a highly compacted mixture of soil or aggregate, cement, and water. Soil cement is sometimes called cement stabilized base or cement treated aggregate base. Soil cement becomes a hard and durable material as the cement hydrates and develops strength. Cement stabilization is done when the compaction process is continuing. As the cement fills the void between the soil particles, the void ratio of soil is reduced. After this, when water is added to the soil, cement will react with the water and it will harden. So unit weight of the soil will increase. Because of the hardening of the cement, shear strength and bearing capacity is also increased. Cement helps decrease the liquid limit and increase the plasticity index and workability of clayey soil. Cement reaction is not dependent on soil minerals, and the key role is its reaction with water that may be available in any soil. The third admixture used for soil stabilization is lime stabilization. Slaked lime, calcium hydroxide, is very effective in treating heavy plastic clayey soils. Lime may be used alone or in combination with cement, bitumen, or fly ash. Sandy soil can also be stabilized with these combinations. The principle involved in lime soil stabilization is the exchange of ions between lime and soil when added. When clay soil is treated with lime, cation exchange takes place between them, which increase plastic limit and reduce plasticity index, which finally results in increased instability of the soil. If clay contains gravel in it, then lime acts as binding material for clayey gravel. Lime changes the nature of the adsorbed layer and provides pozzolanic action. Pozzolanic action is a reaction over time or the reaction rate between a pozzolan and calcium hydroxide in the presence of water. Plasticity index of highly plastic soil are reduced by the addition of lime with soil. This is an increase in the optimum water content and decrease in the maximum compacted density, and the strength and durability of the soil increase. Lime soil stabilized mix are used to construct subbase and base course for pavement. Lime-treated soil is more suitable for warm regions where temperature is very high, and for colder regions it is not very suitable. Lime soil stabilization is suitable for soils like clay, silty clay, clayey gravel, and others, and it is not suitable for granular soil or sandy soil. The illustration shows the step for lime stabilization. The soil which needs stabilization is scarified and pulverized by suitable equipment. Now, add some amount of lime to the pulverized soil, either in powder form or in form of slurry, and mix using suitable equipment. In general, slurry is recommended by better mixing. If lime powder is used, water should be sprayed all over the soil. Next, leave this mixture for 1 to 4 days, since lime soil reaction is slow process and needs some time. After that, add rest of the lime content and mix it for the final time. Spread the soil to required grade and compact it using rollers. Compaction should get required maximum dry density. The compacted lime soil layer is allowed for moist curing for 1 week. Field tests are conducted to check water content and maximum dry density of compacted soil. Next admixture is fly ash. Fly ash is a byproduct of coal-fired electric power generation facilities. It has little cementitious properties compared to lime and cement. Most of the fly ashes belong to secondary binders. These binders cannot produce the desired effect on their own. However, in the presence of a small amount of activator, it can react chemically to form cementitious compounds that contribute to improved strength of soft soil. Fly ashes are readily available, cheaper, and environmentally friendly. Rice horse ash, as another additive, is a pozzolanic material that could be potentially used in soil stabilization, though it is moderately produced and readily available. The RHA would appear to be inert material with a silica in the crystalline form suggested by the structure of the particles. It is very unlikely that it would react with lime to form calcium silicates. It is also unlikely that it would be reactive as fly ash, which is more finely divided. So RHA would give great result when it used as a stabilizing material. The ash would appear to be more suitable lightweight fill and should not present grade. The next stabilization technique using admixture is bituminous stabilization. Bituminous soil stabilization refers to a process by which a controlled amount of bituminous materials is thoroughly mixed with the existing soil to form a stable base or wearing surface. Bitumen increases the cohesion and load-bearing capacity of the soil and renders it resistant to the action of water. Bitumen stabilization can be accomplished by using asphalt cement, asphalt cutback, or asphalt emulsion. The type of bitumen to be used will depend on the type of soil, method of construction, and the weather conditions. In frost area, the use of tar as binders must be avoided because of its high temperature maximum susceptibility. Asphalt and tars are bituminous materials which are used for stabilization of soil, generally for pavement construction. Bituminous material, when added to a soil, it imparts both cohesion and reduces water absorption. Another stabilization technique is thermal stabilization. It is done either by heating the soil or by cooling it. One of the methods of reducing the plasticity of highly clayey soil is heat treatment. This is one of the oldest methods of soil stabilization which has been used extensively by the Australian agencies in making pathways. The heat treatment of soil in situ, a travelling furnace capable of handling large amount of soil at temperature over 50 degrees Celsius, is employed. The heat treatment of pulverized black cotton soil to reduce its plasticity in laboratory was studied in India. The study shows that the soil becomes non-plastic after being heated to about 500 degrees Celsius. Depending upon the method of burning, this will always be a mixture of pulverized soil and clods after heat treatment, which give a good gradation. The CBR values of this material after 4 days soaking would be of the order of 110 to 140%. There is also possibility of further improving the heat-treated soil with cement or bitumen. To increase its reactivity with cement, some raw clayey soil may have to be added to heat-treated soil. The optimum clay content to be added can be determined in laboratory based on compressive strength tests. Under thermal stabilization techniques, freezing of soil can also be done. Cooling causes a small loss of strength of clay soil due to an increase in interparticle repulsion. However, if the temperature is reduced to the freezing point, the pure water freezes and the soil is stabilized. Isoform acts as cementing agent. Water in cohesionless soil freezes about 0 degrees Celsius. However, in cohesive soil, water may freeze at much lower temperature. The strength of the soil increases as more and more water freezes. This method of stabilization is very costly and expensive. This method is used only in some special cases. It has been successfully used to solidify soil beneath foundation. This method is commonly used when advancing tunnels or shafts through loose silt or fine sand. Freezing may cause serious trouble to adjacent structure if the freezing front penetrates this area. It may cause excessive heaving, which the ground move upward, usually associated with the expansion of clay soil, which swell when wet. The freezing method involves the circulation of refrigerated coolant through a series of subsurface pipes to convert soil water to ice. It creates strong watertight material. The material is so strong that it is routinely used as a primary method of groundwater control and soil support for the construction of shafts hundreds of feet into water-bearing soil. The coolant can be brought to temperatures well below negative 150 degrees Celsius. Ground freezing can be achieved by using either a large portable refrigeration plant or liquid nitrogen. This method is suitable for all types of saturated soils and rock, and for soils with a moisture content in excess of 8% of the void. The process of soil freezing with nitrogen, the first is ground is prepared and freezing lenses or pipes are inserted. It, it then insert into a ground a series of freezing tubes to form an ice wall, thus creating an impermeable barrier. The soil is frozen until it forms a stable block of ice. The treatment takes time to develop and the initial costs are high. Therefore, it is only suitable for large contracts of reasonable duration. The freezing tubes can be installed vertically for conventional excavation and horizontally for tunneling works. The usual circulating brines employed are magnesium chloride and calcium chloride with a temperature of 15 to 25 degrees Celsius, which would take 10 to 17 days to form an ice wall. Liquid nitrogen could also be used as the freezing medium to reduce the initial freezing period if the extra cost can be justified. Electrical stabilization. Electrical stabilization of clay soil is done by a process known as electroosmosis. As a direct current DC is passed through a clayey soil, pure water migrates to the negative electrode, which is cathode. It occurs because of the attraction of positive ions that are present in water towards cathode. The strength of the soil is considerably increased due to removal of water. Electroosmosis is an expensive method and is mainly used for drainage of cohesive soil. Incidentally, the properties of soil are also improved. Lastly, we have recycle and waste product. Improved chemical and mechanical stabilization techniques are needed for such waste material as crushed old asphalt pavement, copper and zinc slag, pepper mill sludge, and rubber tire chips. The need to recycle many potentially hazardous materials, it will be necessary to develop a realistic, economical, and effective means of assessing the risk of pollution posed by these materials through research and emissions. In some cases, risk evaluation is hampered by restrictive environmental constraints, and this issue needs to be addressed well. In conclusion, soil stabilization has emerged as a very important and effective for the construction and other purpose. Types of soil are different, therefore, it uses a different methods and material for stabilization. Both surface and subsurface stabilization can be obtained. Stabilized soil can be used in pavement and to support light structure. The treatment with lime and lime columns can reduce both the total and differential settlement and increase the bearing capacity of soil. Global climate change might affect the durability and application of stabilizers. Performance-based testing will be necessary to prove effectiveness of these stabilization agents after it has been applied. That's all for this recorded video. Thank you for your kind attention. I will end the recorded video with the quote from the world top-notch golfer: "You can always be better."